Okay, so let's do a little review here. What we're reviewing is electric field doing work. So, as we remember, the work is defined to be the dot product of the force and the displacement. For an electric field, the force is the charge times the electric field. So now, just as a reminder, to do the dot product, we take and we break the field into two components. So we take the component of the field that's perpendicular to the displacement and the component of the field which is parallel. And when we calculate the work, we just use this part, the part that's parallel to the displacement. Okay, so that's how we calculate the work done by an electric field. Now, if the path is very long, then we need to break the path into a sequence of segments. We calculate the work on each of those segments, and then we add them up in a sum. So we just sum over all the different segments, and that gives us the total work. Okay. Now, the thing is that before we define the electric potential difference between 2 points to be negative, the dot product of the electric field and the displacement. So that's just what we got for the work. So what we find is that the work is negative from the definition of electric potential times the charge times the sum of all the difference in voltages. But we remember that in a closed loop, Kirchhoff's laws tells us that the sum of the voltage differences around the loop has to add up to 0. So that tells us we expect the work done by an electric field, the net work done as you go around a loop, to be 0. And consequently, this electric field dotted with dl. Now we have a special symbol here, right here, which is just the same as this sum, but it's only the sum for a closed loop. So this little circle in the middle is supposed to remind us that it's a closed loop. Okay, so this circle is very important. It reminds us closed loop. So it's just the sum, big S, with a circle on it. Okay, so what we expect is that if we close the loop, then the network should always be done. This sum should always be 0. Now we're going to look at a demonstration here. We have this coil of wire again, and it's connected up to this ammeter. This ammeter is what's called a galvanometer. What's inside there is actually another coil of wire. And that coil of wire is connected to this needle. Next to the coil of wire is a permanent magnet, so that if a current goes through there, there will be a force on that loop of wire, which will cause a torque, and it will move the needle. Okay, it's a very, very simple way of measuring current. So essentially, this is just a long piece of wire. That's all there is to it. There's no batteries, nothing else here. All right, but if there is a current in here, we'll be able to see it by the movement of this needle. Now here we have our magnet with a magnetic field going out that way. Now I'm going to define a direction to this coil. So we have to think about the area of this coil here. Now we decided the area as a vector is either pointing out that way, normal to the surface, or that way. And we have to decide which is the one we're going to pick. And the way we pick it is like this. The way this is hooked up is that if the current goes this way, that will read as a positive current here. So we're going to think of that as a positive current. And the way to tell which way the area goes is by imagining this is the top of a giant jar. So if we take this top and rotate it like that, are we tightening the top onto the jar? Or are we taking it off? Yeah, you don't really have to just put your hand on there. And what would you do if you wanted to open the jar? You go this way, right? So the top of the jar would go this way. So if we go this way, the top of the jar will go that way onto the jar. So that's the direction of the arrow. Okay, you just have to think, you already know, to tighten a bottle you go like that, to loosen it you go like that. You know which way it goes if it's tightening or loosening. Okay, so we're going to call that the direction of this area. So this area, this loop, and a direction vector pointing that way, away from the camera. So we're going to start off by taking this magnetic field and pointing it in that same direction. Okay, so then I'm going to get closer to this. Now, as I get closer to this, the direction of the field doesn't change, but it gets stronger. So the field here gets stronger and stronger. So if I come towards the camera, the magnetic field of this is getting stronger and stronger because you're getting closer to it. So the same thing here. As I get closer, the field will get stronger. So now watch, as I get closer, you can see it went over to the negative side. Try again. I'm going to get closer, if you didn't catch it. When I get closer, you get a negative current. Okay, so the moral here is, notice that if it's just sitting here, there's no current. If I just have it here, there's no current. It's only when the magnet's moving, that is when the magnetic field strength in this area is changing, that we get a current. Okay, so this changing magnetic field is actually producing an electric field going around this direction in this wire, and that's what's pushing the current. Okay, so now let's try, I'm going to turn this around. Now the direction of the area and the direction of the field are opposite. Now if I move closer, I get a positive current. Okay. All right, now let's try one other thing. So we know what happens if I get closer, it goes negative. Now I've got them opposite directions. What happens when I pull it out? So now if I pull it away, the field will decrease. Okay, it's going to decrease in strength in this area. So as I pull away, it gets positive. Okay, and we could try the same thing with the area vector and the magnetic field oppositely directed. If I pull it out, there'll be a decrease in the field strength, and the current is negative. Okay, so we want to remember those things. We'll write them down in a table so we see all the conditions. We could also change the magnetic field direction. So what I've done is I've taken a permanent magnet here and put two of them and clamped them onto a string. Okay, it's actually really wanted to line up with the field of the Earth. So this is a compass. But I can also put that in here and see what happens. So as I turn this, you can see we also get a current. So the field strength isn't changing so much, it's just changing the direction. Okay, so there's different ways we can get this induced electric field in here. And it has to do with the strength of the magnetic field, but also the direction. Okay, so we'll try to clarify all these examples, all boil down to one law, so that should simplify it all. Okay, so what we found was if there is a changing magnetic field, it creates an electric field. And in that case, this integral, the sum of all those E dot dLs isn't zero. It actually does work as it goes around in a closed loop. So the Kirchhoff's law is still okay. Kirchhoff's law applies to electric fields produced by static charges. So that's still fine. It's just that for electric fields that are produced by changing magnetic fields, Kirchhoff's law no longer applies. We'll see a way of saving Kirchhoff's laws in just a minute. Okay, so this sum here, we call it the EMF, the electromotive force. It's a terrible name. It's not a force. It's an energy per charge. It has the same units as volts, but it's not an electric potential either. So it's kind of a funny thing, and it's good to think of it as the product of the electric field and the displacement around the loop. But we usually use this script E symbol here to notate it. Okay, but that's just for the electric field produced by a changing magnetic field. Okay, so it's not equal to zero, but I haven't told you what it is. Okay, so it's somehow related to the changing field, but let's look at a different demonstration now to see exactly what happens here. Okay, so here we have something similar. We've replaced the permanent magnet with an electromagnet. So you have a power supply over here, which is running a current through here. But the current isn't a constant. It increases and then decreases and go the other direction. And to be able to see that, I've put a Hall sensor here in the middle, which measures the magnetic field. Up here on the screen, you can see the field increasing and decreasing. Okay, so now what we're going to do is we're going to use this guy again to see if we can still measure that field. And you can see there it is, needle swinging back and forth like it did before when I increased and decreased the field. Alright, so what we'd like is something a little more quantitative. So instead of using this needle, I'm going to hook it up to the computer. And we can measure essentially how hard, what we call the electromotive force produced by this second coil. Okay. Okay, it's a little bit noisy here. But you can see that there's this current being pushed through there. This is the green one is the amount of, it's like an effective voltage of one turn of this wire. So over here you can't really see the scale, but this is 1/10 of a millivolt, so it's fairly small. Now one thing we notice is that whenever this is going up, this is positive. I've oriented these to the sense of positive is that, again, this area is pointing that way, positive current there. When this is positive, that means the current's going around this way, so that's what we call the area that way. And the Hall sensor is set up for the field in the opposite direction. So the field positive, when this is positive, it means the field's this way. And when this is positive, the current's going that way. Okay, so one thing you notice is that whenever this is falling, this is a negative current. And whenever it's rising, it's a positive current. And it's pretty jumpy, but yeah. So now I'm going to change the frequency of this. Like right now, it's going through a full cycle every second. So it takes a half a second to rise and a half a second to fall. So I'm going to double that. And I want you to look, consider, right now this is roughly going from minus a tenth to plus a tenth of a millivolt. So I'm going to increase this to double the frequency. So now it only takes a quarter of a second to rise and a quarter of a second to fall. And notice that this now goes up to 0.2 to minus 0.2, so it's doubled in amplitude. And if we double this again, let's go up to 4 cycles per second. So now it's even shorter time. This is doubled again. And indeed we find the physical law is that the voltage here is actually the slope of this graph. Now I didn't tell you is I also took in this graph is I multiplied times the area of this loop. So I have the magnetic field strength of this sensor times the area of the loop. So it ends up that the slope of this graph is equal to the value there. So that means if we take this field strength times the area, take the rate of change in time of that, that gives the induced electromotive force or induced voltage on this coil. Okay, so that was sine waves. That was a triangle wave. We could switch this over to a sine wave and see if that still works. This is a little harder to see, so I'm going to change so that we don't have quite so much time on here. Let's just do 1 second instead. And look at the graph. Okay, so you look at it, so it sort of looks, coincidentally, we caught this, right? So it looks like a cosine. Right? Okay, so this is the law of this chapter, actually. This is what we just saw. We have this field here, the magnetic field, times the area of the loop and the rate of change of that product. And that gives us this induced EMF. And we're able to measure that directly with a voltmeter in the computer. So it functions in many ways like a voltage. Okay, so this is what we were graphing, the voltage. And we could see that the rate of change of the field times the area gave us the voltage. All right, so this is called Faraday's law. It's one of the 4 fundamental laws of electromagnetism. And it's just relates, this is like the way you describe how a changing magnetic field leads to an electric field. We're going to stick to cases where B is uniform over the area, just because it's easier to calculate. In that case, this formulation like this is fine, but if the field isn't uniform, then we need to break the area into small sub-areas, each of those a little dA, and then we need to sum all those together. So you just calculate the flux, that's the field times the area, through each little area and add them all up. Now, this negative sign there is we need to resolve that a little bit. Why is it there? And what does it tell us? So this comes back again to this idea about how we define the direction of the area. And it's important that the direction of the DL, what we're calling a positive EMF in essence, if the EMF is positive, it pushes the current around in that direction. That has to be the right direction relative to the area. And like I said before, the best way to think about it is the cap on a jar or a bottle. So if you rotated the cap in that direction, which direction would the cap go? So in this case, the way it's drawn, if this is, you're imagining this is the top of a jar and you rotated it, the cap would come off, and that's the direction of the area. Now, this weird sum over a symbol, this weird symbol of a sum over a loop seems kind of complicated. It's really an integral around a line, so it's called a line integral. And it seems complicated, but fortunately, in a circuit, we can use a crutch. It's a conceptual crutch that simplifies it. And the simplification is to just add an extra battery into your circuit. So if you have some loop, like here in this diagram, if you have some circuit with a loop in it, then you need to, if you know that there's a magnetic field going through that loop and it's changing, then we need to also add this fictitious battery into here. And the value of the voltage on that battery is given by Faraday's law. And then it just kind of, you can forget about the magnetic field and this weird electric field that isn't like a voltage. There's no battery there really. It's not all at one point. It's just a conceptual tool. All we know is that in the net, when it goes around that loop, that it's going to be doing some work in that direction. Okay, so this is the crutch. It's important to remember that it's not actually that way. The electric field is actually spread over the entire loop. It's not just focused in that one place like it would be in a battery. But as far as Kirchhoff's laws now, you can now apply Kirchhoff's laws and it will work out properly. Okay, now let's see how to use these. I'm going to review the area thing one more time because it can seem complicated. All right, so if we lay the loop out flat on the table, it tends to be easier. So let's suppose we do that. And you plop your fictitious battery in there. Okay, you've got two ways you can possibly plop it in there. Now, one would drive a current clockwise, and the other would drive the current counterclockwise. So let's look at each one. And again, I'm going to go back to the cap on a bottle. So in the first case, with this clockwise current, you think to yourself, if I grabbed the top of a water bottle and turned it that direction, would I be tightening it or loosening it? Okay, so just do it with your hands and then you won't have any doubt. You just know. All right, so this one would be tightening, and so that cap would be going down onto the bottle, and so the area is also down, perpendicular to that surface. So we draw it like that. That little X means down. And the other case is coming out, of course. If you turn it counterclockwise, it comes undone, the cap comes off and comes towards you. Okay, so that defines the directions. Now let's go back and see how to use this in the demonstrations that we already saw. So this is the first one. So let's just try to do this really methodically here. So with this direction of the what we called positive, we had to have going clockwise as the direction of our current. So the EMF had to be put in like this. So drive a current around that way. So in that case, the cap would be going away from us, so we know the area vector is pointed into that loop. Okay, so now the first demonstration we did was with the field also going into the loop, and we're getting closer, so the field was increasing. Okay, so this is the first demonstration we did. Now, in this case, the field and the area are in the same direction. So B dotted into A is just the product. They're two vectors in the same direction. If you take their dot product, it's just their two magnitudes. Okay. Now, if B is increasing, then we know that the rate of change of B is positive. So then we can put this together. And we see that this has to be less than 0. It's negative because of the minus sign here. Okay, so this is positive. That's just an area. It's also positive, so altogether it has to be negative. And that's why you can't quite see it in this diagram, but over on, the needle was over there on in the negative direction. Okay. So I'll leave you to do the other cases here, because it's a good exercise. These are the observations. You should rationalize them to yourself using the method that I did here. Okay, so now the second of the second demos, we switched over to using the computer. And basically we need to evaluate the slope of this guy. So you can see that the slope is positive here. We get that positive value. When the slope comes down, we get the negative value here. Okay, to calculate the slope, we need the net rise. You can't quite see it in this, but if you zoom in, you probably can. It's about 0.05 Tesla meter square. Okay, so we know that the change in the field times the area. Remember that in this experiment, I actually calculated, you remember you can make a new calculated column. I used the measured magnetic field multiplied by the area of the loop. So that's what was actually in that graph. Okay, so the net change from the bottom to the top is about 0.05. Now, you should also check that if you take a Tesla times a meter squared, the units are the same as volts times seconds. You can check that by just saying that QVB is the same as QE, they're units-wise. Okay, and go from there. You know the units of electric field are volts per meter. Okay, and the time, we need the time for the rise. If you zoom in here on the oscilloscope, you can see it's 4 cycles per second. So it's a quarter of a cycle, for 1 cycle. It takes half a cycle to rise, half a cycle to fall, so it's 1/8 of a second here for the rise time. So with that, we can calculate this slope, and we get 0.04 volts. Okay. Indeed, if you look at this graph here, it goes from 0.4 to minus 0.4, so that seems to work out. So the other thing we should resolve is that the minus sign. So in this case, the direction we picked for the magnetic field sensor gave a positive number when the field was in the opposite direction to the area. That means that this dot product has a minus sign in it. When you take the dot product of two vectors that are in opposite directions, you get negative the product of their magnitudes. Okay, so then when we put that into our definition of the EMF, that cancels out this minus sign here. So then we just end up with this. And that's why the rate of change of this graph ended up giving us this graph. That's just straight up Faraday's law. Okay, and then the last one. I guess it's not the last one, is it? We had the sine wave. So it was actually really convenient. It just happened to stop when the field times the area looked like a cosine, and the induced electromotive force was negative sine. I went ahead and took off the graph these amplitudes. So the amplitude of this was 0.03 down to negative 0.03, and the amplitude of this was 0.75 volts. Again, the frequency is 4 here, so the angular frequency is 2 pi times 4. All right, so then this is the same configuration, so we still have this, that the dot product is negative, the product of the magnitudes. All right, and then we want to verify Faraday's law, so calculate both sides. We end up with this, as we did before. That's just because of the orientation of the field in the area. We take the derivative of the cosine, it gives us a minus sign. We pick up an omega here from the chain rule. We take the derivative of the cosine, gives you minus sign, then you take the derivative of what's inside. The derivative of omega t with respect to t is just omega. So you can see the minus sign cancels from both sides, and really it gets down to a question of comparing the amplitudes. B is the amplitude of the EMF, and A is the amplitude of the B times A, the flux. Okay, and then plugging in the values that we had, we find that certainly within my ability to read those amplitudes from this graph, that they're the same. There was one other demonstration, and that was the one where I had the magnet spinning in the coil. So in this case, B and A are both constant. What changes is the angle between them. So in general, if you have two vectors, A and B, and they have an angle between them, B dot A is just B times A times the cosine of the angle. So we could do it like this. Now, B and A are constant. The magnet wasn't getting nearer or farther from the loop. The area wasn't changing. So this is minus. We can take the B and A out in front, and then we just have the derivative of the cosine. This gives us a minus sine theta, and then d theta dt. So it would depend, this is the rate at which the angle of that magnet was changing. Okay, so this would, if it was spinning at a constant rate, this would just be a constant number, omega. And so you can see why the needle was swinging back and forth, because theta was changing with time. And so the sign was causing the EMF to swing back and forth.